Swayam Prabha. Digital India. Educated India.
So, in addition to the three-phase system, one of the important topic which is there to convert three-phase to two-phase connection, right? So, Scott connection. Scott three-phase or two-phase conversion or connection. So, let us understand how these connections are made. So, the Scott connection is the most common method of connecting the two-phase to three-phase system or three-phase to two-phase system. So the two transformers which are connected electrically but not magnetically. So one transformer is called the main transformer and the other transformer is known as the auxiliary transformer. So let us look at the connection diagram. So we have one main transformer. Okay. So this is one transformer. So this is known as the main transformer. So now let us mark the values. So suppose this is IA, this is IB, and this is IC. Okay, so these are the three phase values, and this is the V2T and V2M. So this is the main transformer. Okay, so and this is the teaser transformer or the auxiliary transformer. This connection is very important, where it is converting your three phase to two phase conversion, right? So we have A, B, C, two phase, and now we are getting out of this three phases ABC, V2T and V2M. So this is root 3 by 2 NP, this is NS, this is NS, this is 0.5 NP, 0.5 NP. Okay. The current which is going here is I2M, and the current which is going here is I2T, the teaser and the main transformers. So this is the Scott connection diagram. The main transformer is the center tapped, which is at D. So this is the main transformer, which is a center tap transformer and connected across the line B and C. Okay, so this is the line B, this is line C. You can just write. Okay. it has a primary BC and the secondary terminals A1 and A2. Now the phasor diagram, if you look clearly, we can clearly identify the 3-phase to 2-phase conversion. So we can write here VAB, VBC, VCA. The magnitude of all three voltages are same, which is nothing but V line. Okay. Now VBC is nothing but, suppose VBC, we consider this as a reference. So VBC, if we consider as a reference, VL angle 0, then VCA will be VL angle minus 120, and VAB will be VL angle minus 240 degree. Okay, so this is the phasor diagram. This is VBC, VCA, VAB, 120, 240. Okay, so the value of this VB, so in this particular case, when we try to calculate the voltages VBD and VDC, so it appears equal. So the voltage which is equally divided in this part of the winding and this part of the winding, so we can write VBD is equal to VDC, which is nothing but half of the VBC. Okay, because this is a center tap transformer. So VAD, just writing here, VAD is nothing but VAB plus VBD. Now if you add these two voltages, which is nothing but VL angle 120 plus half of VL angle 0, if you add these two, it will be around 0.866 VL angle of 90 degree. So angle of 90 degree means it is vertical. This is VL or VAD, correct? VAD, it is nothing but 0.866 VL. And then we have VBD plus VDC, VBD and VDC. Which is 0.5. Okay. So now clearly here you see the angle between these two is 90 degree. And the VBC is taken as a reference. So this is nothing but VBC. This is total is VBC. So if the turns ratio, this is the primary side of the two-phase. Now you can see the turn ratio is selected very specifically, right? √3/2, and here also it is selected as NS and the 0.5 of the values. So now if you convert this by turns ratio accordingly, so VAD will go to the V2T. So this voltage will get transformed by this transformation ratio √3/2. So V2T is nothing but NS by NAD, which is nothing but into VAD. So this is NS by root 3 by 2 NP into root 3 by 2 VL. So this will get cancelled, this will get cancelled. So it will be around NS by NP times of VL. This is V2T. Now what is V2M? V2M, we can clearly see this voltage will be the voltage transformation ratio. This is nothing but V2M will be nothing but the ratio. So NP by NS into this rated voltage is VL. Okay. So if you look at the magnitude of V2M and V2T, both are same, because the transformer ratio 0.5 NP plus 0.5 NP is total NP divided by NS is the transformer ratio, and the rated voltage is VL. So the VL is basically here is VBC, okay, which is 0 degree, and here this VL will be having an angle of what? AD. So AD is having angle of 90 degree. Okay. So basically V2T, this VL is nothing but VAD having angle of 90 degree. This VL is nothing but VBC having angle of 0. So if you draw the V2T and V2M, so this will be 90 degree and it will lead by main transformer and so this is the transformation. Okay. So this is why the factor of root 3 by 2 was taken, because if you see it comes around 0.866. To neutralize this factor, we take the number of turns in this particular configuration, and these are the central tap transformer where the 0.5 or the 50% turn ratio is taken for the main transformer, and root 3 by 2 is the turns ratio for the teaser transformer or the auxiliary transformer. So with that, we close the topic of three-phase transformers. So now onwards we'll be considering the motors, the rotating machines. So we'll start with the DC motors and then go to the induction and the synchronous machines. So with that, we close the AC three-phase transformers and the Scott connection. Dear students, in this lecture we are going to study the DC machines. Okay, so DC machines basically are having two kind of functionality depending upon the generator or the motor. So before going to the generator or the motor part, let us first understand the basic structure of electric machine. Okay, so here you can see one figure which I have taken from the Google for a better understanding. So you see, in electrical machine there are consists of two parts. Okay, so every electric machine has two parts. First is the rotor, and the second is stator. Rotor is the rotating part, and the stator is the stationary part. So in this figure you see the outer part is the stationary part. So this is stator. So this is the frame, and the inner part, which is nothing but the rotor. Okay, so this portion is nothing but the rotor. So the stator and the rotor, these are the magnetic poles were extruded, which are basically stationary, and this rotor is rotating. So stator and rotor are basically separated by an air gap. You can see this gap. This is the air gap. Okay, so this air gap is separating the stator and rotor. Okay, so the stator and the rotor are separated by an air gap. With these, the stator and the rotor, they are made from the ferromagnetic material. So they are made of ferromagnetic material. Okay, they are made of ferromagnetic material. So in general, if you see, the stationary part is the outer part where the motor is being fixed to some structure or some body. Okay, but depending upon the application, suppose if you see the ceiling fan, so in that case the electric machine is the such a way that the outer part is rotating, the fins or the fan blades are rotating, right? So internal part is stationary, which is attached to the shaft hanging on the roof, on the ceiling. So in that case you see that different application, but in general most of the motors which you'll see, the internal part will be considered as the rotating part, which is here in this example also. This is the rotor, and the outer part is stationary, which is stator, and these are the slots. These are the slot. Basically some section is made for the conductors to fit in. So slots are being cut at the outer periphery of the rotor. So this is a rotor, so outer periphery of the rotor is this one, so there slots are cut, and the inner periphery of the stator, so this is the stator, so inner periphery slots are being cut. Okay, so the winding in which the voltage is induced. So what is an armature? Armature is a winding in which the voltage is induced. Okay, so the winding is basically the conductors which are being placed in the slots. So these are the slot which carries some conductors which are connected in a specific fashion, which forms a winding, and those windings having a voltage induced in that, then those conductors are known as the armature. Okay, so the winding through which a current is passed to produce the main flux is called the field winding. So we'll have field winding. So these windings are basically in which the current is passed. So in which current is passed to produce main flux. is known as the field winding. And in case of a DC machine, permanent magnets are used for some machine, or somewhere we use electromagnets as the field producing windings. So normally it depends on application what voltage or the power rating of your machine is, but we can use the permanent magnets as well as the windings to produce the main flux. So main flux can be produced by permanent magnets or windings carrying current. Okay, so these are some of the basic definitions. So there are two types of DC machine, as I mentioned. One is DC generator, and another one is DC motors. So these are the two types of DC machine. One machine is converting the mechanical input to the electrical output, which is generator, and the motor converts the electric input into the mechanical output. Okay, so the DC generator is based upon the principle that when conductor is rated to rotate in a DC magnetic field, a voltage is being generated in the conductor using. So before going to that, let us first understand. So the principle is, when there exist three things, right? First we have field, second conductor, and third is a relative motion between them. Okay, relative motion between the two. Then we have a induced voltage. So when we have a field windings with then conductor, and then we have a relative motion between them, then we generate the voltage. So this is the basic idea. But whenever there is a rotating DC magnetic field and a conductor is being placed, the voltage is generated, then it goes to a generated side. Or when we have a field and we rotate the conductor, like using mechanical like you have turbines or you have other resources, prime movers, then we have some kind of motion between the two, right? The conductor is being rotated in the magnetic field, or magnetic field pushes the conductor to rotate, then it becomes the motor. So the construction basically has two parts. One is the magnetic field system. Okay, so the field is basically the magnetic field system. The second is the armature, which is conductor, and third is the commutator and the brush, which basically the terminal part of the machine or the DC machine. So first let us understand the magnetic field system. Okay, it means there should be some kind of winding or magnetic permanent magnetic material which should produce some magnetic field in which the conductor should move, which will induce the voltage. Okay, so the magnetic field system is stationary part of the machine. So as we see this basic structure, so the permanent magnetic field is being produced by the stator winding. So this is the stator. Winding. So here basically you see the field winding. Okay, it is mentioned here, right? So this is the shaded or the gray color portion you are seeing is the field winding, which produces the magnetic field. The outer frame is a hollow cylinder. Okay. So basically you see this is basically a kind of this. This is the machine, right? This is the motor. This is a cut section. So it is a hollow cylinder which is cut. Inside that we have pole cores which are bolted to the yoke. So this is known as the yoke. Okay. The outer frame is known as the yoke. So yoke basically supports the pole. Poles are basically these: north, south, north, south. These are the poles. And you see that there are poles which are being made in a specific shape. Okay. So it basically supports the windings which are being placed in the on the poles, and the projected poles are known as the salient poles. So these kind of poles are known as the salient pole machine. So this is basically 4-pole machine. So each pole core has pole shoe. So this is the pole shoe. I mean the terminal of the end part of the pole is known as the pole shoe. It has two. Okay, so it has two functions. One is it supports the field winding, and the second is it increases the cross-sectional area. Of the magnetic circuit and reduces its reluctance. Okay, which results in the lower reluctance circuit of this magnetic machine. So the pole coats are made up of again kind of lamination to avoid the eddy current losses in the material. So each pole core has one or more than one field coils or the windings which are placed over it, as I have marked here. So whenever the current is flowing through these windings, it produces a magnetic field, and then it turns into the field coils, right? So the field lines, if you want to see, the field will be emanating from the north pole, going to the rotor, and then attracted by the south pole, and then it will again go back to the north pole. Similarly, this is the field lines which will be generated by the field coils. So the field will be, okay, let us change the color so that you can see it clearly. So this is the field line. Okay, and then similarly go here, to rotate in this direction, north to south, north to south. Okay, so this is the kind of north this way, then it is going to north this way, then. So this is how it will be rotating in this fashion. Okay, armature I told you already, the rotating part of the DC machine is called the armature, where the voltage is being induced and which is taken by the terminals by using the third portion, which is nothing but the commutator or the brush gear. So one of the important part of the machine is commutator. Sorry. Okay. So the AC voltage is produced in a coil rotating in the magnetic field. Okay. And to obtain the DC part in the external circuit, so what will happen? The converted voltage, the output voltage, so there are two voltages. One is the generated voltage in winding, because one side north pole will be approaching, and when the south comes, this voltage will go to the opposite polarity, and again north comes, again it will be going to the opposite polarity. So it will change the polarity between like when it is being approached by the north pole or the same conductor is being approached by the south pole. So the generated voltage in the winding will be AC. Now we have to convert this AC into DC, so that function is being performed by the commutator. Okay, so to obtain the direct current or the DC as the external circuit, we need a commutator. So commutator converts the generated AC into DC quantities. Okay, so this is the purpose of generator. So the current, basically what happens, the current is being collected alternatively by using carbon brushes. So this brush gear, basically the arrangement where the your current collection happens. Okay, so this is about the construction of the DC machines. Now, okay, where we have seen the field lines also. So now we'll see the equivalent circuit of a DC machine. Okay, equivalent circuit of a DC machine. So the armature of a DC generator can be represented by a equivalent electric circuit. Okay, so it is being represented by three sections or the three connected elements. How? So suppose this is your motor, this is represented as the motor, and the voltage is being generated across some armature. Okay, so this can be represented by a generated EMF E, then some drop in the resistance, and then some drop in the brush and gear where the current collection happens. Okay, so this is the kind of equivalent circuit of a generator. So this is your machine. I'll write M is not motor. Okay, I'll write machine. So any electrical machine, if it is generator, the armature will be having a voltage E, then some drop in the armature RA, and the current will be flowing as IA. Okay, and this is the voltage drop VB. So we have three quantities here. We have E, we have RA, and we have VB. E is the generated EMF. Then we have armature resistance. And then some drop, voltage drop. At brush contact. Because it's not 100% electrical drop connection. So there will be some voltage drop which is being incorporated as VB. If suppose this is a motor. Now in case of a motor, it will take current IA which will go to the armature. Then there will be some voltage drop. Okay. Then they drop some resistance. It will get drop here. Then remaining drop will happen in the armature. So this is E. Okay, so this is a kind of equivalent circuit. In both the cases, you can clearly understand that the current direction is reverse and the voltage drop in the brush terminal has been changed when it is represented as a motor or a types of DC motor if you want to consider now. So let us write the type of DC motors. So based upon the magnetic flux in a DC machine, the production of magnetic flux in machine by circulating the current which is being fed in the field windings are called the excitation. So based upon that excitation, we'll be going to categorize the machines or the DC motors into the different types. So the production of magnetic field, first we write the excitation, the production of the production of magnetic field or flux in the machine by circulating current in the field winding. Is known as excitation. And based upon the method of excitation, the machines are, we have two categories. First is separate excitation. Another one is the self excitation. Okay, so there are two types of excitation. So in separate excitation, we have a separate source, energy source. Okay, then the self DC source, but in self excitation the current flowing through the field winding is supplied by the machine itself. So in the separate excitation we have a different source, and in the self excitation we have the same machine supplying the field or the current to produce the field winding, in the field winding to produce the flux. Okay, so the direct current machine are named according to the combination of field windings. Okay, so we'll have now the main types of the DC machines. First is separately excited DC machine. Second is shunt, somewhere it is known as shunt wound, or like only shunt machine. The third one is series wound or series machine. Or the compound machine. Now we'll see one by one what these machines are meant, what is the naming of this machine means. So let us first consider the separately excited DC machine. Okay, in a case of separately excited DC machine, the field coils are energized by a separate DC source, and the connection of the separately excited DC motor can be represented by the following. So when you have a motor, okay, so this is your machine, okay, where this is armature and the generated EMF is shown here. It is basically a rotating. Now the field excitation for this will be represented by a field coil which is excited separately. This is a representation of a separately excited DC machine. So when we talk about the generator, the polarity of E will be, V will be this one, and the direction of the current will be outside, and this field winding will be having a current IF. Okay, and the supply will be given separately. Where is in the case of a electric motor, the field winding will be having the same kind of arrangement where it is supplied by the separate DC source carrying current IF in the field windings, and then we have a motor which is taking current from the supply V, which is IA, the armature E, and the polarity will be given like this. Okay,